Good morning, students. Today we are going to discuss the next topic, that is called electric field. Okay, or electric field, or we can simply say it as a electric field intensity. Also, we can say it is representing with the letter capital E. Let us see what is this electric field. To understand this, let us consider. I am considering one charge. Suppose say this is a positive charge. Its electric field at a particular point, suppose say this is a point, how much electric field it has at this point. That means how much electric field strength at this point it has, that we have to calculate. Electric field means electric field due to this charge. That is how much electric field or how much electric field intensity, how much strength of electric field is there at this point. That's what we have to calculate. So that is called electric field. So how to define this? To define this, at a particular point, I have to assume that a unit positive test charge. Suppose say I am assuming a unit positive test charge at this point. Say this is the distance r. Whatever the force experiencing by this unit positive charge due to this bigger charge, that force acting on that charge is called its electric field strength at that point. Suppose say if I consider another point here. At this point again I will consider one more unit positive test charge. Now if you see, the force acting by this charge on that charge will be less when compared to this. That means at this point the electric, suppose say this is the point B, say this is the point A. At this point, say that is electric field A. Electric field at a point A, say that is EA. Electric field at a point B, say that is EB. So that means as we move away, then what happens means the electric field gradually decreases. That means the force experiencing by this charge due to this charge also decreasing. So as we move away, the force experiencing by that positive charge will be decreasing. So that force acting is called electric field or electric field strength or electric field intensity also we can say. So how to define that means electric field at a particular point is nothing but force per unit positive test charge. So this is called what? This is the definition of electric field intensity. What is electric field intensity? Force experiencing by unit positive charge at a particular point will give that electric field intensity. So here the force is more. That means more electric field intensity. Here force is less. So that means here less electric field intensity. So that means here we can say that here EA should be greater than that of the EB. That means this charge electric field at a point A is greater than that of its strength at this point. So this charge electric field strength here is greater and its charge electric field at this point will be less. Okay. So this electric field strength is defined as, how to define this? Charge electric field is nothing but force experiencing by unit positive test charge. So this is called what? Definition. Now let us see here what is actually unit positive test charge. What is actually unit positive test charge? Within the name itself is the unit positive test charge. Unit means one value. That means the charge whose magnitude is of 1 unit, which is very smaller, and but because of its presence, another electric field, that means another charge's electric field does not affect. That means this charge does not affect any electric field, or we can say that this charge does not affect the electric field of any other charges. Generally, if suppose two charges we are taking, okay, so if you place this charge beside the another charge, then what happened? These two electric field may repel or may attract, basing on the whether they are positive or whether they are negative, or one is positive, one is negative, right? So here the electric field strength, they may change, or they may repel each other, or they may attract each other. So here, if you place in front of any one of the charge, if you place this unit positive test charge, then that charge electric field does not change. Why? Because its magnitude is very small. That means it's the electric field which it is creating. This is very weak. It does not affect on any other charges. Got it? So such small positive charge is called what? Unit positive test charge. Right now, this is the electric field intensity, we can say. So E is equal to F by Q. So if you want to write it in vector form, then we can say that E bar is equals to F bar by Q naught. What is F bar? F bar is nothing but it is the force between these two charges. Force between these two charges. Its unit. What is the unit for this? Its SI unit is. We know that this is Newton, this is Coulomb. So I can say Newton per Coulomb is nothing but is the SI unit of this electric field. And it is a vector quantity. It is a vector quantity. So in which direction this electric field will be? The electric field will be in the direction of electric force. See, this is repelling that side. That means in this direction the force is there. That means it is repelling this positive charge in that direction. Then in this case, its electric field will be towards along the same direction as that of the F. F direction and E direction both will be in the same direction. Suppose say if I am taking this as a negative charge, then this unit positive charge will be attracted. That means the F will be in this direction. That means force of attraction will be in this direction. In that case, the electric field will be also in the same direction toward this zone. That means we can say that electric field will be always in the direction of electric force only. So this is, we can call it as a vector quantity. Clear? Now let us have a small derivation like for this electric field intensity. Let us consider this is a charge, positive charge. Here I wish to calculate the electric field intensity at a particular point P, which is at a distance, say this is R from its center. To calculate the electric field intensity at this point, what we have to assume? We have to assume there a unit positive test charge. So let us consider here, I have assumed a unit positive test charge. Therefore, from the definition, what is the definition? From the definition, we can say that force per unit charge is called what? Electric field at that point. Okay, so that's what I am going to calculate. So before that, as these two are the two charges, they are separated by a small distance r, then we can say that a force is said to be acting between them. Therefore, force, or we can say that Coulomb force between these two charges is given by F is equals to 1 by 4 pi epsilon naught into Q, that is Q naught divided by R square. We know this very well. We know this formula very well. Say this as equation 1. Therefore, from the definition of electric field, as we know that from the definition of electric field, E is equals to F by Q naught. That is, force experienced by this unit positive test charge is called its electric field. So that's what I am going to calculate. E is equals to F by Q naught. Therefore, F means we know this formula 1 by 4 pi epsilon naught into Q naught by R square whole divided by Q naught. So therefore, this Q naught will get cancelled. What is left here? E is equals to 1 by 4 pi epsilon naught into Q by R square. So we are getting electric field intensity at this point in terms of this charge is nothing but 1 by 4 pi epsilon naught Q by R square. So electric field at this point due to this charge, in terms of this charge and in terms of this distance, we can write this is the formula. So this is also one more formula here. So finally, we are having a formula. E is equals to, we can say that F by Q naught, or also that is equals to 1 by 4 pi epsilon naught into Q by R square. So this is what we can say that formula we can say. Now, this is nothing but here this value will give the magnitude of electric field intensity at this point due to this charge. Now, I can write that one in terms of vector form. To write in vector form, what we have to write? One more term we have to include there. What is that? That is called R cap. As we know that I cap, J cap, and K cap are the unit vectors along X axis, Y axis, and Z axis. Similarly, here the electric field will be in this direction. That is, since this is positive, it is repelling this side, this one. Therefore, the electric force as well as electric field both are in the same direction. We can say. So, therefore, in this direction, electric field is said to be there. So, this I can write here R cap. I can say that this is a unit vector which represents the direction of electric field. Therefore, I can write here E bar is equals to, that one we can write 1 by 4 pi epsilon naught into Q by R square into R cap. And since we know that, what is R cap means? Since we know that R cap is nothing but is equals to R bar by mod R. R cap is nothing but unit vector. Unit vector is nothing but mod of R bar by mod of R. So now if I substitute that value here, we can write 1 by 4 pi epsilon naught into Q by R square into R. R cap is R bar by mod R. Therefore, E bar is equals to 1 by 4 pi epsilon naught into Q R bar by R cube. This way, this one both will become R cube. So therefore, I can write this one as a R bar. Separately, I am writing. So these are all multiplication only. So finally, we can say that 1 by 4 pi epsilon naught into Q by R cube into R bar. So now this is called vector form of electric field. So this is called what? Vector form of electric field. So this is called vector form of electric field, and this will give the magnitude of electric field. Got it? Fine. Now, next topic we are going to discuss about the next topic, that is called principle of superposition of electric field. What is principle of superposition? As we have seen previously, principle of superposition of electrostatic force. What does that mean? If a n number of charges are distributed, then the force experienced by any one of the charge is nothing but is equals to the vector sum of all the forces acting due to remaining n number of charges. So the total force acting on any one of the charge, that vector sum of all the forces is said to be a superposition. Superpose means to add up all. So similarly here also, electric field or electric field intensity at a particular point due to n number of charges are distributed in a space is nothing but is equals to the vector sum of electric field due to these n number of charges will give the total electric field at that particular point. So this is called principle of superposition of electric field. So let us see this. Principle of superposition of electric field. Let us consider a n number of charges of magnitude Q1, Q2, Q3 and so on up to Qn are distributed in a space. Let us say Q1, Q2, Q3 and so on like this, Qn. These are the n number of charges are distributed in space. Here I wish to calculate the electric field intensity at a particular point. Suppose say this is a point. This is the point at which I wish to calculate the total electric field intensity due to these n number of charges. Let us say first charge is at a distance of, say, this is R1. Similarly, second charge is at a distance, say, this is R2. Similarly, the third charge is at a distance, say, this is R3. Similarly, so on. Now, nth charge is at a distance, say that is Rn. Therefore, what is the total electric field at this point? This will have an electric field at this point, say that is E1. Similarly, this will also have electric field at this point, say that is E2. So here one more thing. To calculate the electric field at this point, what we have to assume? We have to assume a unit positive test charge. So this, if suppose this is positive, then this will repel that side. So in this direction, the electric field will be. This is the electric field direction E1. If this is Q2, if suppose this is also positive, this one also will repel that side. That means this is the direction of E2. Say this is E2. Say this is E1. Similarly, suppose say this is also positive, then in this direction it will also repel. Say that is E3. And so on. Similarly, if suppose this is also plus, if suppose any one of the charge, suppose it is negative, then it will be attracted. Then the electric field will be towards that charge. If it is positive, away from the charge. If it is negative, the direction will be towards the charge. Okay. Let us say I am taking that also positive. Then this will also repel in this direction. So therefore, here the total electric field at this point is given by the vector sum of all these electric field intensities. Therefore, electric field intensity at this point is nothing but the vector sum of, that means E bar is equals to E1 bar plus E2 bar plus E3 bar plus so on plus En bar. What is E1 bar? Just now we have written there. Just now we have written before that in a vector form we can write this one 1 by 4 pi epsilon naught into Q1 by R1 cube into R1 cap. So here R1 is nothing but R1 cap is nothing but unit vector which shows the direction of electric field E1. Similarly, if I take R2 cap, this will represent the unit vector for the E2 direction. Similarly, if I write here R3 cap, this will give the unit vector for the E3. So in this way we can write. Okay. So this is for first one. Similarly, we can write for the second one. 1 by 4 pi epsilon naught Q2 by R2 cube into R2 cap plus 1 by 4 pi epsilon naught into Q3 R3 cube R3 cap, and so on. We can write for the final one 1 by 4 pi epsilon naught into Qn by Rn cube Rn cap. So this how we can say that the electric field at this point is nothing but vector sum of all the electric field due to n number of charges. This can be written in a more simpler form as we have written in a previous case also. This can be written as in terms of summation. That means we will make it in a short form. That is, we can write this one. E is equals to here. This we can take common 1 by 4 pi epsilon naught. We can take common here. 1 by 4 pi epsilon naught. If I take common, then remaining what is left here? Q1 R1 cube R1 cap. Similarly here Q2 R2 cube R2 cap. Q3 R3 cube R3 cap. Similarly, so on Q1 Rn cube Rn cap. So in this way, all are 1, 2, 3, 4 like this are there. So many are there. So this I can write in a single in one general form. So I can write this one in terms of summation of 1 means here instead of 1 I will write I by Ri cube Ri cap. So this is we can write in a general form. Therefore, where I is nothing but is equals to 1 to n. See there 1, 2, 3, so on up to n are there. So I is equal to 1 to n. So this is the expression for a electric field intensity E cap E bar. So electric field intensity E bar is equal to 1 by 4 pi epsilon naught into summation of I1 to n Qi by Ri cube into Ri cap. So this will give the total electric field intensity at this point. If you take 3 charges, suppose 3 charges are there, then here 1, 2, 3. That means here we can take Like this, we can take only 3 we can take. Got it? So this is the general expression for a electric field intensity at a point by superposition principle. Got it? Now, electric field line. Now, what is electric field line? What is actually electric field line here? So, electric field line is nothing but it is the path on which if you place a unit positive test charge, that unit positive test charge will tends to move. So, that path is called electric field line. To understand this, let us say this one. Suppose say this is a positive charge I have taken. Okay. So if I place here unit positive test charge, suppose I have placed here, what will happen? It will repel that one. So this will move away from this charge. So this will move in this direction. So this line is called electric field line. So electric field line is nothing but it is the path on which if you place a unit positive test charge, so it will tends to move freely. So that path is called a electric field line. Suppose say this charge if you place here, then this will repel in this direction, linearly outward. If you place the charge somewhere here, then again it will move in this direction. So in this way, we can draw such many lines around this charge. So for positive charge, positive will repel each other. So therefore the electric field lines are coming outside this way. So here electric field lines is nothing but it is the path on which if you place a unit positive test charge, that test charge will tend to move away from the charge. So those paths is said to be electric field lines. Clear what I'm saying is? Similarly, suppose if you take a negative charge, suppose say if you take a negative charge. Now you place just unit positive test charge. If you suppose if you place it, what will happen? This unit, this is negative, this is positive. It will attract this one. So that means it will come in this direction towards this charge, attracting. So electric field line is in this direction. So this path is nothing but it is the path in which this charge is free to move. So that line is said to be an electric field line. Clear? Suppose say similarly if you place this charge somewhere here, still it will attract in this direction. So this is a path in which this charge will move. So in this way we can draw such many lines. In this way we can draw many lines around this charge. So these lines are called electric field lines. So again, once again I tell what is electric field line? Electric field line is nothing but it is the field line is nothing but it is the path on which a unit positive charge if you place, that unit positive will tends to move. Either it move away from the charge or it may be move towards the charge. That depends upon the nature of the charge, whether it is positive or negative. Clear? So that's why you can say that positive charge always we can say that electric field line emits outside. Whereas the negative charge always electric field line will tends to move towards it. That is, it terminates towards the negative charge. Electric field line originates as the positive charge. Again, I once again repeat. Electric field line originates at the positive charge and terminates at the negative charge. Keep in mind this, right? And here, this electric charge, this electric field line is there. This electric field line is a vector quantity. Why? This is having a particular direction. In which direction it is? So electric field line is a vector quantity. It is showing very clearly. We can say that it is having a particular direction. So, and if you consider such points, suppose 1 point, 2 point, 3 point, 4 point, 5 point. Suppose here I have taken 5 points. So if you see carefully, At this point, the electric field is how much? At this point, electric field is how much? At this point, how much? If you see, the electric field at a near point will be maximum, than this, than this, than this, than this. So that means as we move away, the electric field gradually decreases, as we have seen previously. So electric field intensity gradually decreases. Suppose this is 1, 2, 3, 4, 5. I have taken up 5 points. So in this case, electric field at a point 1 is greater than the electric field at point 2. It is greater than this. It is greater than this. It is greater than this. So that means as we move away, the electric field gradually decreases. And when you reach somewhere at infinity, suppose if you go somewhere at infinity, then what is the electric field at this point? Means at that point, the electric field will be 0. At infinity, electric field will be 0. Clear? So here, this field, the electric field lines will give the, in one way we can say that these electric field lines combined will give the strength of electric charge. That means electric charge, how much strength it is having to repel any other charge. How much strength it is having, that strength is represented. That is electric field strength or the electric field intensity. How much is there? That will represented by this electric field line. Clear? Now, let us draw some electric field lines for different charges. Sometimes they may ask this for a 1 mark. Let us see. Suppose as we have seen just now, a positive charge, if you take, electric field lines will be like this. Always radially outward. Keep in mind that always it will be radially outward only. If you take a negative charge, then always it will be towards the charge. Like this, always towards the negative charge. Suppose say I am taking a, suppose say this is charge Q and say this is also charge Q. This is minus Q, this is positive Q. If suppose, keep in mind, if suppose both the charges are equal in magnitude, that means the number of lines should be also equal. For example, let us see here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. For this, let us see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. One more we have to draw, say that is 12. Again 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there are 12 lines are there. So whenever the magnitude of charge is equal, means we can say that the number of field lines should be also equal. Suppose say I am taking one more. Suppose say I am taking a bigger charge. Say this is capital Q. Here capital Q I am taking. For this I am drawing here. Here plus Q is nothing but here this is greater than this charge. Suppose say this charge is greater than this charge. Therefore, for this charge, we have to draw number of lines should be greater than this. If it is 12 means it should be more than 12. Let us draw that also. That means electric field line should be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So in this way, now here we can say that the number of electric field lines are increased than this. Why? Because its magnitude is greater. If the magnitude is greater, then electric field line increases. That means electric field strength of this charge is greater than this, we can say. Similarly, for negative charge of the same like this only we have to write. But the only the thing is this direction should be towards the inward. So that is what we can. That's what we can draw. Now let us see. Suppose one is positive charge is there of same, and one more is say this is negative charge. So these are the two charges are there. Placed beside each other. Then how to draw the electric field line for this? We know that electric field lines start from the positive and terminates at negative. So this is the electric field line. So now this was the diagram for plus Q and one more is minus Q. So plus Q minus Q charge, if they are placed beside each other, that means in one way we can say that this is the diagram for a dipole. Dipole is nothing but two charges which are separated by a small distance, equal in magnitude. If there are two charges of equal in magnitude are separated by a small distance, then such system is said to be an electric dipole. So such dipoles, field line we can draw like this. So magnitude is same. So that's why the field line also should be same. So here if you calculate 1, 2, 3, 4, 5, 6, 7, 8, 9. For this also 1, 2, 3, 4, 5, 6, 7, 8, 9. So here also 9 lines are there. Here also electric field line 9 are there. So in this case, this is what we can say that of same magnitude. Suppose say if you are taking up two different magnitudes are there. Let us see. Suppose one is of bigger charge capital Q and one is of suppose say small q. This is of bigger charge, say this is of smaller charge. Then electric field line we can draw like this. So if you see carefully here, we can say that here see, if you see here 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. So here again we are getting same as this only 9 lines record. Now, in the similar manner, if you see for this is a bigger charge, definitely it should have a large number of electric fields. So for this we can draw like this. So some more we have to draw. So here if you see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So something near about 13 is there. So this is of 13 lines electric field line, here only 9 electric field lines. So whenever if suppose for one of if they ask of two different magnitudes, one of bigger and one of smaller one, draw the electric field line is in this dot we have to write. Similarly, if these both are said to be unlike charges, suppose if you go for a like charges, let us see for the like charge. This is of capital Q and one more is small q we have drawn. Suppose both are positive charges are there. If I draw for both positive charge, if both positive charges are separated by a small distance like this only, then how will be the diagram? Let us see. This is plus Q, this is one more plus Q. As we know that positive will repel each other. Then the electric field lines will diverge from each other. Here they are converging, that means they are attracting. There they will diverge. Why? Because they will repel each other. So therefore I can say here the electric field line which are coming like this, they will diverge like this. This one also they will repel and they will diverge. So if you see carefully, the number of field line for this 1, 2, 3, 4, 5, 6, 7, 8. For this also 1, 2, 3, 4, 5, 6, 7. So electric field line for both are equal. Here also equal only, but they are converging, they are attracting. That is, they are diverged, means they are repelling each other. So that this is how we can draw the diagram for like charges. This is for unlike charges. See, if you take two different magnitude like this, if you take for them, suppose say one is taken. In the similar manner, instead of positive, if I take two negative, then also we have to draw same like this only. Only the thing is here, the arrow mark will be towards the charge. Why? Because negative charge, as we know that arrow marks will be towards the charge. So here also, if you write minus q and minus q, if you draw for them, only we have to draw the same like this only. Only the thing is the arrow line will be, it should point towards the charge. That's all. Clear? Now come to the point. Next one. One is of bigger charge. One is of bigger charge and one is of smaller charge. Suppose for these two charges I am drawing again. Then for this, if I take a bigger charge here and one is of smaller charge, if you take, then again here also same. This will repel that charge. This will also repel that charge. It will be also repelled. So in this case, its strength is more. So its repulsion will be more. So that's why the null point. Suppose the both charges are equal, then the null point will be at the center. That means between these two charges at the midpoint will get the null point. What is null point? Null point is nothing but it is the point at which electric field intensity is 0 or the net electric field intensity 0. Means if you consider here unit positive test charge, that won't experiences any force. Why? Because if suppose this is acting a force on it that side, the same amount of force experienced by this charge due to this charge also in this side. This both will be get cancelled, and we can say that net force acting at this point due to the unit positive test charge is 0. Okay, so that is called null point. So that null point will be at midpoint if both the charges are of equal magnitude. If suppose these are of two different magnitudes are there, one is greater one, one is smaller. So in this case, the null point will be shifted towards the smaller charge. Why? Because this will repel. Suppose say if I consider a unit positive test charge at this point, then this will repel that charge toward that side. That will also